Transmission towers are slender and high structures constructed in every region and climate. So, environmental loads such as wind loads are principal loads acting on the transmission line. On the other hand, the vibration of cables under wind loading is a major reason for the transmission line collapse. In this paper, stability of the transmission line was numerically studied under wind load. Failure analysis of the transmission line have three steps. In step 1, wind load was numerically modeled. The structure was modeled in second step by finite element method. Third step is analysis of the transmission line with a three-step analyzing method. Result of this step was used for defining failure modes of the tower and suggesting suitable retrofitting method. The line is located between Urmiye and Khoy cities in the southwest of Iran. A 400 kV LT-tip self-support lattice transmission tower. The configuration of the transmission tower was shown in this figure. Numerical model of the line consists of 5 towers with 6 similar spans equal to 400 meters that was modeled using Abacus Sapphire. Moreover, fixed supports were used at two ends of the line. Suspension V insulator were used to connect three aluminum steel reinforced conductor cables to the tower. Moreover, two steel ground cables were put on the top of the tower. The members of the tower are made from high tensile steel with yield stress equal to 350 megapascal. The material nonlinearity is included in the analysis assuming elastic perfectly plastic behavior. Also, the von Mises failure criteria is used. The tower members were modeled using 4 3D beam elements. A 3D nonlinear stress-strain material model was applied in the analysis of the transmission line. Also, 3D nonlinear truss elements were used for modeling cables and insulators. The properties of cables and insulators was shown in this table. The wind loads on the panel points and cables nodes are computed by formula of guidelines for electrical transmission line structural loading of IASS. Wind speed could be divided into two parts, mean speed and turbulence wind speed. Variation of the mean speed with height is often expressed by logarithmic form. Power spectral density concept is used to simulate the fluctuating of the wind. Theoretical and numerical PSD for a point with a height of 9 meters from ground level was computed in this figure. As shown in this figure, there is a good agreement between the numerical power spectral density and the theoretical results. The analysis of transmission line was started with an initial static nonlinear analysis under gravity loads. Then a nonlinear time history analysis was applied in 2 steps. Quasi-steady analysis for mean wind speed, dynamic analysis for the fluctuating component by Newmark method with time interval less or equal 0.01 second. In this analysis, damping of the tower was applied by Rayleigh damping method and aerodynamic damping for cables. These figures show wind speed time history in the studied region. Incrementally dynamic analysis of the transmission line was started from wind speed equal to 20 meters per second at reference point 8. Furthermore, the lateral deflection of the top point of the central tower of the line was recorded in the analysis. The tower fluctuates around the equilibrium condition of the mean wind speed equal to 20 meters per second at the reference point for the whole time of the analysis. Then, wind speed at the reference point was increased incrementally up to 23 meters per second. In that case, the deflection of the top point of the tower abruptly grew to a large value at the time about 12 seconds from wind loading application on the transmission line. This figure shows the failure in the central tower of the line for wind speed equal to 23 meters per second at the reference point. In that case, yielding of bracing members caused instability in the central tower of the line, and this failure propagated into a large part of the tower. The cross-section of initial failed members of the tower were increased to improve its performance by back-to-back connecting an angle section with the same size of the failed member as shown in this figure. Afterward, the analysis was repeated for wind speed equal to 23 meters per second. This figure shows the deformation of the central tower after retrofitting of the mentioned failed members under the wind load with a speed of 23 meters per second. Also, the retrofitting members was resisted under this critical wind loading condition. Failure of the other members around the middle height of the tower could make it unstable. Retrofitting was repeated for these members and transmission line was analyzed again. This figure shows lateral deflection of the top point of the retrofitted transmission line under the wind with a speed of 26 meters per second in the reference point. It can be concluded that the retrofitted tower is stable under the wind speed of 26 meters per second at the reference point. This study shows that the traditional design methods of the transmission tower could not suitably include the dynamic effect of the wind load. The proposed technique could be applied to predict the exact capacity of the transmission line under the wind load. This technique can be used in the design of modern transmission lines and to recognize the weakness of the used towers. Thank you a lot.